There are 5 questions in total, and the total time allotted is 3 minutes. All the questions are multiple select questions, meaning that there may be more than one option which can be correct. Time begins now. Time's up. Now we will see the solutions. According to Einstein relation, for any semiconductor, the ratio of diffusion constant to mobility of carriers. You know that according to Einstein relation, we have diffusion upon mobility to be equal to kT divided by Q. So the first option is depends upon the temperature of the semiconductor. Therefore it is true. Depends upon the type of the semiconductor. So this is false. Varies with lifetime of the semiconductor. This is false. Is a universal constant. This is also a false statement. Direct bandgap semiconductors exhibit short carrier lifetime. Short carrier lifetime is actually true, since there are no trap centers or recombination centers in direct bandgap semiconductors. They usually have short carrier lifetime as compared to indirect bandgap semiconductors. So this is false and this is also false. Direct bandgap semiconductors are not used for making BJTs. Direct bandgap semiconductors are actually used for fabricating lasers. So the C option is correct. Under high electric field in a semiconductor with increasing electric field, we have studied this topic and also have drawn two different graphs, one for mobility and other for velocity with respect to electric field. And you know that initially mobility is independent of electric field, but under high electric fields the mobility of charge carriers begin to decrease. And also, you know that drift velocity is equal to mobility into electric field. At very high electric field, mobility is inversely proportional to electric field, which actually gives drift velocity to be a constant. Therefore, drift velocity at high electric fields begin to saturate. So, the C option is also correct. Now for the fourth question, it is said that the silicon sample is doped with 10 raised to the power 16 phosphorus atoms per centimeter cube. Phosphorus is acting as a n-type semiconductor for silicon. Therefore, we will represent it with Nd, which is equal to 10 to the power 16 per centimeter cube. Similarly, boron atoms will act as p-type semiconductor. Therefore, we will represent it as Na. It is provided that dopants are fully ionized. It is clearly visible that Na is greater than Nd. Therefore, the semiconductor is p-type and hole concentration will be given as you should know that intrinsic carrier concentration is of the order of 10 raised to the power 10. Therefore, in the under root term, we can ignore Ni square. It will give the whole concentration to be equal to Na minus Nd divided by 2 plus Na minus Nd divided by 2. So we can say that the whole concentration will be approximately equal to Na minus Nd. So the whole concentration comes out 10 raised to the power 16 per centimeter cube. So the B option is correct. Now for the fifth question, which is actually very much related to fourth question. It says the concentration of ionized donors and acceptors in a semiconductor are Nd and Na respectively. If Na is greater than Nd and Ni is the intrinsic carrier concentration, the position of the Fermi level with respect to intrinsic level depends on. From the fourth question itself, we found that the value of P0 is equal to Na minus Nd. And also, we have a formula for finding hole concentration with respect to intrinsic carrier concentration, which is P0 equal to Ni into exponential of intrinsic Fermi level minus Fermi level of the p-type semiconductor divided by Kt. If we replace P0 with Na minus Nd, then we will get intrinsic Fermi level minus Fermi level of the p-type semiconductor equal to Kt natural logarithm Na minus Nd divided by Ni. So, the position of the Fermi level with respect to the intrinsic level depends upon Na minus Nd. Therefore, A option is correct.